Hi, welcome for our lesson for today. This is organic chemistry. It is a subject that blends basic chemistry, logic problems, 3D puzzles, and stick figure art that looks like something you may find in a prehistoric cave. To say that organic chemistry covers a pretty large amount of material is a bit like saying that oxygen is pretty important for human survival. Organic chemistry does cover a lot of material, so much you can't possibly hope to memorize it all. But good news, you don't need to memorize the vast majority of the material if you understand the basic concepts at a fundamental level, and indeed, memorization beyond the basic rules and convention is even frowned upon. The catch is that you really have to understand the concepts. You have to practice by working a lot of problems. Mastering organic chemistry without working problems is impossible, just like the kind of architect which do not bother to draw up any plans. Life as we know it is based on organic chemistry. Here, we can have the four major biomolecules: lipids, nucleic acids, carbohydrates, and proteins. But we will start at the foundation. We will start at the less complex structures. Most of the advances in pharmaceutical industries are based on a knowledge of organic chemistry. Many drugs are organic compounds. We have rofecoxib. It is a COX-2 selective nonsteroidal anti-inflammatory drug. It was marketed by Merck and Company to treat osteoarthritis and other kinds of arthritis, acute pain conditions, migraine, and dysmenorrhea. Atorvastatin, or Lipitor, is a medication prescribed by a doctor to lower cholesterol in people who have been diagnosed with high levels of this. Oxycodone belongs to a class of drugs known as opioid analgesics. This medication is used to help relieve moderate to severe pain. Benzylpenicillin, also known as penicillin G, is an antibiotic used to treat number of bacterial infections such as pneumonia, strep throat, or syphilis. It is also important to note that living things are made up of organic chemicals. Proteins make up hair, the DNA, and foods and our medicines. We have to also take note of the origins of organic chemistry. Its foundation date from mid-1700s. Compounds were obtained from plants and animals, and scientists then had a difficulty because these compounds have low melting points. They are very hard to isolate, purify, and work with. Organic compounds were considered to have some vital force as they were from living sources, much like saying that they have their own spirits. And so, they thought that organic compounds can only be taken from living things. They thought that organic compounds cannot be synthesized or made in the laboratory. By 1816, Chevreul found that soap can be separated into several organic compounds which he termed as fatty acids. By 1828, Wohler showed that it was possible to convert inorganic salt, ammonium cyanate, into organic substance, urea. Therefore, organic chemistry has evolved. This now pertains to the study of carbon compounds, which comprise of more than 50 million known chemical compounds. And this is because carbon is part of group 4A. Group 4A can share 4 valence electrons and form 4 covalent bonds. The elements found in group A, which is carbon, are able to bond with another to form long chains and rings. This carbon is the only element also that has the ability to form immense diversity of compounds. We can see here in these slides that all of these are made up of carbons. Organic compounds are those compounds found in any organism that is living or was once living containing carbon. Compounds lacking carbon and not from living organisms are referred to as inorganic. Hence, we say that carbon is the element of life. Carbon's unique atomic structure allows it to covalently bond up to four other atoms. Carbon is the simplest element on the periodic table that has four valence electrons, and carbon is neither electronegative nor electropositive. Most organic compounds have a skeleton that is composed of C-C bonds. The C-C bonds may be single bonds, double bonds, or triple bonds. The skeleton of an organic compound has H's attached to it. Other heteroatoms like oxygen, halogens, or nitrogen may be present as well. Let us examine now how carbon becomes so special. The number of bonds formed by carbon in an organic compound is determined by its electronic configuration. Its electronic configuration is 1s2, 2s2, 2p2. Carbon has four valence electrons, therefore. And we also see that carbon generally forms four equivalent bonds. Now, why is it four equivalent bonds? We saw in the previous slide that carbon uses an s orbital and two p orbitals. So therefore, there should be a discrepancy on how the orbitals of carbon should look like. But experiments have already proven that it is actually four equivalent bonds. The formation of the four equivalent bonds is best explained using the concept of hybrid orbitals. So we look at the valence shell of carbon. We have 2s2 and 2p2. Notice that at the 2p orbital, there is a vacant orbital. So we can promote one electron from the s orbital to the vacant p orbital. So if we can do that, we will have one s orbital and three p orbitals. But again, that here comes the question that why are the bonds of a carbon equivalent? Because there is what we call hybridization. So in hybridization, we mix the s orbital and the two orbitals together to form what we call the sp3 orbitals. sp3 orbitals means that there is one electron in the s and three electrons in the p orbitals. And we mix that together, hence we have sp3. We now look at how the sp3 orbitals are formed.
A carbon atom has four valence electrons. Two of them are paired and located in the 2s orbital, but the other two are unpaired, occupying two of the three available 2p orbitals. When during reaction one s electron is excited to a p orbital, there are four unpaired electrons available to form covalent bonds. The single 2s and three 2p orbitals hybridize to give four equivalent 2sp3 hybrid orbitals. Overlapping of the hybrid sp3 orbitals with the s orbitals of four hydrogen atoms produces four sigma bonds. The resulting methane molecule has a tetrahedral geometry. The bond angles are 109.5 degrees. The shape of the molecule is in accordance with the experimental results and the predictions from the VSEPR model.
So that explains now our hybridization. So now we know that there is an sp3 orbitals for the structure of methane. So we have an s orbital and three 2p orbitals. We have that hybridized and we get four equivalent sp3 orbitals. Okay? We also saw that the bond angle is 109.5 and the shape is a tetrahedral. Each CH bond has a strength of 439 kilojoules per mole and a length of 109 picometers. So let's now take a look at a worked example. Let's draw a bond line structure for propane and predict the value of each bond angle and indicate the overall shape of the molecule. So the one that you see there at the upper right corner is the line bond structure of propane. So as we can see, all are single bonds. So if all are single bonds, then we can say that the geometry is tetrahedral around the carbon atom and the bond angles are approximately 109 degrees. Carbon can also obtain an sp2 hybridization. For an sp2 hybridization, there is an unfilled p orbital that is perpendicular to the plane. So for sp2 hybridized orbitals, this leads to the formation of double bonds. And the most common sp2 hybridized structure is what we call the ethylene. Ethylene contains two carbons. It has two sp2 hybridized orbitals that overlap to form a sigma bond. The p orbitals interact by sideways to form the pi bond. The sp2-sp2 sigma bond and the 2p2p pi bond result in sharing of four electrons, leading to the formation of the double bond. This is the structure of ethylene. The hydrogen atom forms s bonds or sigma bonds with four sp2 orbitals. The CC double bond in ethylene is shorter and stronger than the single bond in ethane. Let's take a look at this example. What if we are to draw the electron dot line and bond line structures of formaldehyde? We also have to indicate the hybridization of the carbon orbitals. So for the solution, two hydrogens, one carbon, and one oxygen can combine only in one way. The orbitals are sp2 hybridized. Let's now take a look at the third hybridization possible for carbon. This is called the sp. sp orbitals is when carbon forms a triple bond sharing 6 electrons. Carbon 2s orbital hybridizes with a single p orbital, giving two sp hybrids. Two p orbitals remain unchanged. sp orbitals are linear, therefore you have 180 degrees apart on the x-axis. This is how we visualize the sp hybridization. The most common carbon compound that has an sp hybridization is the acetylene. This is the simplest carbon compound containing the sp orbital. So again, let's review. Bonding in acetylene involves a 180 distance or 180 degrees distance around the carbon-carbon bond. Now let's compare the C-C bonds and the CH bonds in methane, ethane, ethylene, and acetylene. This table shows us the comparison of bond strengths for methane, ethane, ethylene, and acetylene. We can see here that the bond strength for triple bond in acetylene is 231 kilocalories per mole. That is very high compared to the 105 kilocalories per mole for the single bond of methane. So if we will have to arrange the following, the weakest bonds will be attributed to the single bonds, followed by the double bonds, and followed by the triple bond. In our next example, let's draw a bond line structure of propyne and indicate the hybridization of the orbitals on each carbon. We should also predict the value of each bond angle. So the one that you see at the lower left portion is the bond line structure, and we see here that there are single bonds and also the very distinct triple bond. The triple bond will have an sp-sp hybridization for each of its carbon. However, the third carbon that we labeled as carbon number 3 will have an sp3 hybridized carbon orbital. For the bond angle, we can also say that the sp-sp angle will be close to 180 degrees, while the sp3sp will be as close to 109. So let's take a look at hybrid orbitals and carbon as a summary. When carbon forms four single bonds, sp3 hybrid orbitals are involved in tetrahedral geometry. When carbon forms a double bond, sp2 hybrid orbitals are used, and we have a trigonal planal geometry. When carbon forms a triple bond, sp hybrid orbitals are used in linear geometry. For bonding in organic compounds contain not only CC bonds, but they also contain CH bonds. CC and CH bonds tend to be nonpolar because there is a small difference in electronegativities. Most, but not all, organic compounds are relatively nonpolar. They are generally not very soluble in water. Hence, we call them hydrophobic. For the structural formulas, when we write a simple chemical formula such as CH4, we are actually writing what we call a molecular formula. Molecular formula shows the atoms and number of atoms involved in a molecule, but nothing else. In organic chemistry, it is more useful to show structural formulas instead. A structural formula shows each type of atom and how they are arranged in a molecule. So we have here the comparison of molecular formula, a structural formula, and a 3D structure. But we will be learning this in the laboratory. Here are some familiar organic compounds. We have acetic acid, ether, ethyl alcohol, and aspirin. If you notice, all the carbons have four bonds around it. You will never see an organic compound with carbon having five bonds around it. We'll also be looking at carbons with three bonds and two bonds in the laboratory, but they are not stable. And lastly, for the solubility of organic compounds, the very simple rule is like dissolves like. Polar compounds will dissolve in polar solvents, while nonpolar compounds will dissolve in nonpolar solvents. That is the end of our lesson.